Howdy, my name is Adam Garcia, and the technical session I chose to do my research report on is the detection estimation 2. So the reason I chose this topic was because of its mention in developments in maritime radar detection. Traditional radar used today on aircraft is the side-looking linear array radar, um, which is a phase array, so it's mounted onto an aircraft. And as you can see in this picture here, it sends a beam out, and once that beam is reflected back to the antenna, it calculates the depression and azimuth angle, providing the direction of the target. This is great for homogeneous environments. Of course, it's in the air. The noise and clutter is very consistent, and the target is also usually far from clutter. This is the exact reason why this won't work for the maritime industry. In the maritime industry, or in the ocean, there is, it's a very heterogeneous environment. So the strange weather that happens, being able to detect a target vessel from waves, and also being able to detect friendly vessels from the target. So a advanced signal processing technique that has been developed is the multi-stage Wiener filters, or the MWF. This suppresses clutter using orthogonal projections or stage-wise clutter cancellation. So it takes in the signal and it kind of splits it in takes the target steering vector, so the direction of the target, and outputs a desired signal. And then what this B block does is it's a blocking matrix, which outputs the observed data. This will then be sent to this H block, which takes the previous desired signal and tries to output a similar desired signal as closely correlated as the previous desired signal, and then sends that to another B blocking matrix, outputting another observed data. Um, this keeps happening until it gets to the final Wiener filter, which takes in all that data and outputs a matrix providing the data for the target. This technique allows for low sample support, um, robust to clutter variation, and target clutter proximity depending on the estimator you use, and less computations. Right here, this graph is a graph of the MWF. Right here, it's a signal to interference ratio graph. Of course, the higher the interference, the lower the probability of detection, and the higher the signal is compared to the interference, the lower the probability of detection, and the higher probability of detection. Okay, right here is just the sample data provided to the MWF. As you can see here, you don't want too little or too many stages. Too little stages allows for clutter within the desired signal, and too many stages allows for noise when calculating the desired signal. So you want to be able to use an estimator that finds the correct amount of stages for the MWF. And what is being developed are 3 different types of estimations. This first one, embedded minimum description length, or embedded MDL, is actually an earlier estimation technique that was in development, which aims to minimizing the model complexity and data mismatch. It basically tries to simplify the output data from the clutter observed, or until there is no clutter observed. The issue with this is it overestimates, so it allows too much noise into the signal, therefore lowering the probability of detection. Um, and it does this because it doesn't use the string vector in the NWF, so it kind of wastes the use of the MWF when it uses the MWF. Um, this next estimator is the target focus estimation or estimator, which selects stages based on how much clutter energy is in the same direction as the target direction. So it tries to differentiate the two. The issue with this is if the target is too close to the clutter, you might consider the clutter a part of that desired output signal, therefore underestimating the amount of stages. Uh, and then the third technique is the multi or mutual information. What this does is it tries to makes the clutter and desired signal completely independent, so no clutter at all within the signal, based off a feedback system that it uses. So it takes that desired output signal, sends it to the previous orthogonal subspaces, and then outputs a signal. As you can see here, the MI is the best performing of the three, um, with a higher probability of detection than the other two estimators. Thank you.